So next time you are like sitting in a hospital waiting room, I want you to take a really close look at where the windows are placed.
Yeah, just look around.
Right. Notice the exact angle of the glass. Or, observe how the hallway curves before it actually reaches the reception desk.
Because none of that is an accident.
Exactly. Those details were not chosen by an artist trying to just make the room look pretty. They were likely calculated by an algorithm.
Oh, absolutely. Cross-referenced with behavioral psychology.
Right. And specifically designed to reduce your blood pressure by, exactly 3 points before you ever even see a doctor.
It is wild when you think about it.
It really is. I mean, you are walking through invisible, weaponized psychology every single day.
And it's entirely invisible to the naked eye. But the walls around you are just saturated with data.
Yeah.
Every square inch of the built environment is the result of these fierce battles over resources, physics, and, well, human behavior.
We've got this massive stack of architectural texts, and we are going to shortcut your way to being incredibly well informed about how the buildings you live, work, and heal in are actually conceived and constructed.
It is a lot of ground to cover.
It is. We are breaking down everything from ancient architectural theory and the psychology of human-centered design to the raw physics of new materials.
And the digital stuff, too. Computational parametric algorithms.
Right. Plus, the messy reality of what happens when humans actually move in, which is where it gets really fun. I'm so glad to have our resident expert here to help synthesize this mountain of information.
Happy to be here. Because, when you start pulling on the threads of how we build our world, you realize architecture is essentially the process of decoding human existence and then pouring concrete over it.
Huh. That is a great way to put it. Okay, so to understand the cutting edge of where architecture is going today, we actually have to start with a puzzle that has been driving builders insane for 2,000 years.
Oh, the classic triad.
Yes. There is this foundational concept in the industry called the architectural triad. Way back in the 1st century BCE, a Roman architect named Vitruvius codified this as formatus, utilitas, and venustas.
Right, which translates to durability, utility, and beauty.
Exactly.
Basically, a building has to stand up, it has to be useful for whatever task it was built for, and this is key. It has to delight the human senses.
Which sounds simple enough.
It does. And for centuries, balancing those three things was the ultimate goal. I mean, you can see that perfect static balance in the geometry of Greek temples.
Right, or the unbelievable engineering of a Roman concrete dome.
Exactly. It was a very neat, very contained way of looking at the world.
But then the Industrial Revolution happens and just blows that neat little world apart.
Oh, completely shatters it.
We suddenly had mass-produced steel, huge sheets of plate glass, and cities that were just exploding in population.
Yeah, the scale changed completely.
Right. And by the late 19th century, the architect Louis Sullivan drops this incredibly famous mantra. He said, form follows function.
Form follows function.
And for the modernists, that became a rigid law. I mean, if you are building a shoe factory, the purpose of that building is rapid industrial output.
The function is basically just a machine.
Exactly. Therefore, the form should look exactly like a highly efficient machine. 0 gargoyles, 0 decorative columns.
Just pure efficiency. But the problem is, form follows function only works perfectly if the function is static.
Right.
Like a factory makes shoes. That is a definable, unchanging function. But modern society just doesn't operate in those neat little boxes anymore.
Okay, let's unpack this because this is where it gets complicated. If I am asked to design a modern public high school today, what is the function?
It's not just one thing.
Exactly. It has to educate teenagers, sure, but it also has to act as a community center on weekends.
And a designated storm shelter.
Right. It has to accommodate shifting local zoning laws, and oh yeah, it needs a carbon neutral footprint. That is not a static function at all.
Not even close. In the industry, they call this a wicked problem.
A wicked problem.
Yeah, it's an issue with no clear boundaries that constantly evolves while you are trying to solve it.
So designing a building today sounds less like drawing a pretty picture and more like trying to solve a Rubik's Cube where the stickers change colors every time you turn a side.
That is exactly what it is.
But wait, is form follows function actually a bit too rigid for the wicked problems we face today?
Oh, it shatters completely.
Yeah.
If we connect this to the bigger picture, a wicked problem means the target is always moving. You cannot just dictate a solution from a drafting table in an ivory tower when the ground beneath the building is constantly shifting. To solve a wicked problem, the architect has to fundamentally abandon the idea of a standardized, idealized user.
Because there is no such thing.
Exactly. Humans are spectacularly messy, irrational creatures. You have to stop designing for an abstract user and start designing with the actual complex people who will inhabit the space.
So what does this all mean for the actual design process? Because this friction is exactly what triggered a massive pivot in the industry toward design thinking, right?
Yes, exactly.
It's this philosophy centered on user-centered design, breaking the process down into 5 stages. Empathize, define, ideate, prototype, and test.
Right. Which completely rewires the architect's brain.
I mean, instead of having a brilliant eureka moment and sketching a masterpiece on a napkin, you start with empathy.
But empathy in architecture isn't just like feeling bad for someone.
No, it's a rigorous data gathering phase. You shadow people, conduct psychological interviews, and map out their behavioral pain points.
Maggie's centers in the UK are just the perfect manifestation of this.
Oh, I love this example.
Right. So these are cancer support facilities. Historically, when you walk into a hospital or clinic, you are greeted by this massive high reception desk.
Right, the classic hospital entrance.
And that desk immediately establishes a power dynamic. The person behind the desk is the authority, and you are the vulnerable patient.
Wow. Yeah. It subtly spikes your anxiety the moment you walk through the sliding doors.
Which is the exact opposite of what a cancer patient needs.
So by using user-centered design, the architects for Maggie Centers just threw out the reception desk entirely.
Completely gone.
Instead, when you walk in, you walk directly into a domestic-style kitchen with a large wooden table.
You aren't a patient checking in. You are a guest being welcomed into a home for a cup of tea.
It fundamentally alters your psychological state. And we see the same behavioral mapping in the Seattle Public Library, too.
Designed by OMA.
Right. For a century, libraries were designed around the Dewey Decimal System, books on the bottom floors, quiet reading rooms up above.
But OMA actually mapped out the noise and movement of modern patrons.
Yeah, they realized people actually come in to use computers, talk in groups, have meetings, so they flipped the entire building upside down.
Literally upside down.
They put the silent book stacks on the upper floors and placed the loud, active, chaotic public spaces down below.
They let the messy human behavior dictate the physical structure, rather than, forcing the humans to behave according to a predetermined structure.
But wait, if you just ask everyone what they want through user-centered design, doesn't that lead to absolute chaos? I mean, design paralysis.
It definitely can if you do it wrong.
Like, if I ask 100 teenagers what they want in high school, I'm going to get requests for a water park and a zero-gravity chamber.
Huh.
How do you avoid a watered-down design-by-committee disaster?
Well, that is the exact trap that amateur designers fall into. They mistake user-centered design for, like, taking orders at a restaurant.
Right, just writing down whatever people say.
Exactly. But what's fascinating here is where the second phase of design thinking comes in the define phase.
Okay.
Henry Ford famously said that if he asked people what they wanted, they would have said a faster horse.
Right, because the public doesn't know what is architecturally or technologically possible.
Exactly. The architect's job isn't to build the feature the user literally asks for. It's to synthesize those diverse, conflicting desires and extract the underlying need.
Oh, I see. So the teenager asking for a water park is actually just expressing a need for an unstructured, kinetic social space.
Precisely. The architect shifts from being a traditional master builder who dictates the form to a systems thinker who translates psychological friction into physical space.
Okay, translating psychology into space sounds poetic, but gravity still exists.
Unfortunately, yes, gravity is still a thing.
Right, once you synthesize what people actually need, you have to figure out how to stand it up against the wind, which brings us into the iterative design cycle and the sheer physics of materiality.
You can't just go from a sketch of a kitchen table to pouring 2,000 tons of concrete.
Exactly, you have to prototype. And an architectural prototype is essentially like a crash test dummy for physics.
You built to fail, so you can fail safely on a small scale before actual lives are on the line.
And a massive part of that testing comes down to material choices, right?
Absolutely. There's this old modernist concept championed by architects like Louis Kahn called material honesty.
Material honesty. I like the sound of that.
It basically means you shouldn't lie about what your building is made of. If a wall is holding up the roof using the compressive strength of concrete, let it look like raw concrete.
Right, don't cover it in decorative plaster.
Exactly. Let the structural integrity be the aesthetic.
But the palette of materials architects are being honest with has exploded. We aren't just choosing between brick, steel, and concrete anymore.
No, the options are wild now.
Look at cross-laminated timber or CLT. For a long time, if you wanted to build a high-rise, you had to use steel or concrete because normal wood bends, warps, and snaps under that much weight.
Right.
But with CLT, they take layers of timber and glue them together, but they alternate the direction of the wood grain by 90 degrees for each layer.
And by crossing the grain perpendicularly, you eliminate the wood's natural weak points.
It suddenly achieves the sheer strength and load-bearing capacity of structural steel.
But it's entirely renewable and acts as a massive carbon sink.
Which is incredible, and here's where it gets really interesting. We are even seeing biomaterials like mycelium.
Oh, the mushroom bricks.
Yes, architects are literally growing bricks out of mushroom roots. They take agricultural waste, introduce mycelium spores, and the roots act as a natural glue.
It binds the waste into a dense, solid block that can be baked and used as insulation or interior wall paneling.
That blows my mind. But the ultimate test of material innovation has to be Shigeru Ban's Christchurch Transitional Cathedral in New Zealand.
Oh, what a stunning project.
Right, a devastating earthquake destroys the city's main cathedral. The community needs a gathering space immediately to grieve and rebuild, but there's no money and no time for a 10-year stone masonry project.
So Ban designs a towering, beautiful A-frame cathedral out of recyclable cardboard tubes.
Cardboard tubes for a permanent feeling public building.
It sounds impossible.
It does. Prototyping sounds like a dress rehearsal before opening night. But how exactly do you prototype a whole cathedral made of cardboard without it collapsing during the test? Like, how does it not just melt into a puddle the first time it rains?
Right, or get blown over. Well, it comes down to geometry and chemical coatings. The cardboard tubes are incredibly dense, and they were coated in waterproof polyurethane.
Okay, so they treat the cardboard.
Exactly. But more importantly, the structural stability comes from the A-frame geometry. The tubes are acting in pure compression, basically leaning against each other.
But to ensure that would actually work in the real world, they couldn't just build a 50-foot cardboard arch and hope it didn't fall on someone?
No, definitely not.
Huh.
This requires intense interdisciplinary collaboration and hybrid prototyping. You build a physical model to test the chemical waterproofing of the tubes.
But you use digital stress testing to calculate the physics.
Exactly. Another case study from the text, the Eden Project in the UK by Grimshaw Architects, is the perfect example of that digital testing.
Oh yeah, those massive domes.
Right. They were hired to build these massive geodesic biome domes, think giant interconnected transparent golf balls sitting in a clay pit.
Wow.
You cannot build a physical scale model of a biome that perfectly mimics how a sudden 80-mile-per-hour crosswind will affect thousands of individual hexagonal panels.
Yeah, you'd spend millions of dollars just on the physical prototypes.
So instead, they brought in structural engineers and used advanced digital modeling to simulate decades of weather patterns in a matter of hours.
They subjected the digital biomes to snow loads, wind shear, and thermal expansion.
Until they found the precise geometric lattice that could distribute the stress evenly across the entire surface. Physical and digital iteration allows them to just fail fast safely.
Okay, so digital prototyping lets us test a giant greenhouse against a hurricane. But there is a ceiling to that collaboration, right? Well, a human brain, even working alongside a team of 50 engineers, can only imagine so many variations of a dome.
We hit a biological limit on how many structural, environmental, and spatial variables we can juggle in our heads at one time.
Which is exactly when architecture had to stop drawing and start coding.
Right.
When the math outpaces our biology, we turn to algorithms. This is the digital frontier.
We are talking about parametric design. In the past, an architect drew a static shape. They drew a rectangle, and that was the window.
Right.
But with parametric software like Grasshopper and Dynamo, you do not draw the window. You define the parameters.
Is it the rules?
Exactly. You tell the software the angle of the sun at 4:00 p.m. in November. You tell it the average wind speed coming off the ocean. You tell it the maximum heat load the air conditioning can handle.
And you are setting up the environmental conditions, and the algorithm generates the geometry that perfectly survives those conditions.
It is basically applied evolutionary biology.
The building evolves to fit its exact ecological niche. A spectacular real-world application of this is the Al Bahar Towers in Abu Dhabi.
Oh, this one is wild. They built these twin skyscrapers in the middle of a blazing desert environment, which usually means massive air conditioning bills and miserable glare.
But instead of just installing thicker glass, the architects designed a dynamic, responsive facade.
The exterior of the building is covered in this geometric skin made of PTFE fiberglass umbrellas.
And these aren't static panels, they are hooked up to linear actuators and sun sensors.
Right. As the sun moves across the sky over the course of the day, the individual umbrellas physically fold and unfold like massive mechanical origami.
It literally tracks the sun to block the glare, reducing the solar heat gain by 50%, while still letting natural daylight into the rest of the building.
The building is no longer a static object. It is a responsive, kinetic machine.
And it goes even further. With generative design, an AI can process the zoning laws, the budget, and the square footage requirements, and spit out 10,000 optimized variations of a floor plan in 3 seconds.
It's unbelievable speed.
We have extended reality, where you can walk through the AI's best option in VR before a single shovel hits the dirt. We even have construction robotics, like the SAM 100.
Oh, the bricklaying robot.
Yes, it's an automated, laser-guided robot that can lay bricks 3 times faster than a human mason. But I have to push back here.
Okay, let's hear it.
If an AI is using generative design to spit out thousands of optimized building iterations, does the architect just become an editor? Are we losing the human touch in all this math? If everything is just an algorithm chasing maximum efficiency, don't we end up with deeply sterile, soulless cities?
This raises an important question, and it is the existential crisis facing the field right now.
Yeah.
There is a heavy critique of this movement, often labeled parametricism.
Parametricism.
Right. Critics look at these mathematically perfect, algorithmically generated structures and point out that they often end up looking like identical, monotonous blobs.
Right, because a computer program doesn't naturally care about human scale.
No, it doesn't care that a brick wall is textured perfectly for a human hand to brush against. It doesn't understand cultural memory or the historic vernacular of a specific neighborhood in Kyoto versus a neighborhood in Brooklyn.
Because you can't code nostalgia into an algorithm.
Exactly. The algorithm is a brute force optimization engine. The crucial takeaway is that the AI does the heavy lifting of the math, but the human must set the parameters.
Ah, I see.
The architect's role evolves from drafting the lines to authoring the rules. The human is the ethical, social, and aesthetic firewall.
If you don't constrain the AI with human values, it will build a perfectly efficient prison instead of a neighborhood.
Exactly right.
So we have algorithms generating responsive facades, we have dynamic materials, we have an incredibly complex design thinking process, but how do we actually know if any of this works?
That is the big question.
I mean, once the ribbon is cut and the champagne is poured, how do we know the building doesn't secretly make everyone miserable for the people and the planet?
That is the most uncomfortable question in architecture. And the answer is post-occupancy evaluation, or POE.
It seems so obvious, but it is rarely done rigorously.
No, it really isn't. POE is the process of going back to the building a year or two after people have moved in and critically measuring its actual performance against what the algorithm promised.
It's about accountability.
Yes. And this is deeply tied to the evolution of sustainability. We talk about the triple bottom line of sustainability, environmental, social, economic.
Right. For a long time, green building just meant ticking boxes on a LE certification checklist.
You used recycled carpet and low-flow toilets to get a plaque on the wall.
But the industry is finally shifting from doing less harm to regenerative design.
Right. The idea that a building should actively heal the surrounding ecosystem.
The Bosco Verticale in Milan is a stunning success story of this.
Oh, the vertical forest.
Yes. It's a pair of residential high-rises that function as a vertical forest. The balconies are structurally reinforced to support massive amounts of engineered soil.
They hold over 900 large trees and thousands of shrubs.
It isn't just a green roof. The entire facade of the skyscraper is a living, breathing lung.
It actively filters urban dust, absorbs massive amounts of CO2, and has brought birds and insects back into the center of a heavily polluted city.
But post-occupancy evaluation is also brutal because it exposes failure. And the texts point to a legendary failure in the UK called the BED-ZE project.
Oh, BED-ZE.
It was designed to be a completely carbon-neutral housing development. The architects used brilliant passive solar design, relying on super-insulated walls and triple-glazed windows to trap ambient heat so they wouldn't need central heating.
Right, the math was flawless.
Yeah.
The models predicted 0 carbon emissions.
Until the humans moved in.
Exactly.
You have this incredibly sophisticated passive thermal envelope designed to capture the body heat of the occupants and the heat from the oven, trapping it perfectly.
But then a resident decides they'd like the smell of fresh rain in December.
Or they just feel a bit stuffy, so they manually prop open a triple-glazed window.
And the thermal envelope breaks. The heat rushes out.
The apartment gets freezing, and because there's no central heating, they go out and buy cheap, inefficient electric space heaters.
The post-occupancy evaluation revealed massive problems with overheating in the summer and blown energy budgets in the winter.
It's so ironic. We spend years using AI and design thinking to build a smart community, but BED-ZED shows we sometimes forget to teach the actual humans how to live in it.
I agree completely. And that failure is arguably more valuable than a success. BED-ZED proves that you cannot separate the technology from the sociology.
Right.
A building is not a static product. It is an ongoing, living system, a relationship between the structure and the occupant. True sustainability requires the humans to actively participate in the system.
Which leads directly into the concept of the circular economy.
Yes.
Regenerative design ultimately means we have to stop viewing buildings as permanent monuments and start seeing them as temporary banks of materials.
You have to design for disassembly.
Right. If you glue all those materials together, they end up in a landfill in 50 years. If you bolt them together, they can be unbolted, taken apart, and the steel, the CLT, and the glass can become the raw materials for the next project.
Ensuring the feedback loop of design, evaluation, and reuse never actually closes. It is an endless cycle of iteration.
Wow. So, bringing this all back to you listening, the next time you push through the heavy glass doors of a hospital, or find a quiet desk in a library, or sit in your own office, look at the walls around you.
There you go, Lan.
Look at the way the light hits the floor. You are not just looking at drywall and glass. You are standing inside a physical manifestation of deep human empathy.
You are surrounded by the output of incredibly complex parametric algorithms and the legacy of relentless, iterative failure and success.
You are standing inside a machine that was meticulously designed to understand you.
It really is incredible when you frame it that way.
And here's a lingering concept to ponder as you go about your day. The sources mention buildings using AI, sensors, and smart materials to dynamically adapt to their users.
Right. They're watching how we move, how we group together, and how we change the temperature.
Exactly. So, if our built environment is becoming a learning responsive system that gathers behavioral data on us every single day, will there come a day when a building gathers enough data to iteratively redesign itself without the architect?
Now, that is the ultimate evolution of the wicked problem.
Something to think about.